we take it as axiomatic that atoms and molecules cannot react unless they collide with each other, and we are primarily looking at chemical reactions. I try to emphasize this all the time. So essentially we are looking at electronic exchanges and not going all the way down to the nuclei. Of course there are exceptions to situations like where we have to have molecules and atoms collide with each other. You could have thermo reactions that are sensitive to temperature, or in thermal response like decomposition, thermal decomposition, or you could have photosensitive reactions and so on. Okay, so let's now look at what's called the law of mass action. We'll just proceed systematically here. So as an example, if you now take the hydrogen oxygen reaction, so we could now think about a change in the number of moles of hydrogen in terms of a decrease, and therefore we have a negative 1 could be equal to a change in the number of moles of oxygen divided by a negative half, because for every 1 mole of hydrogen that decreases you have only half a mole of oxygen that decreases, and that could be equal to then the change in the number of moles of water divided by +1 to indicate that this is a gain as opposed to a loss for the other two. So the sign and the value in the denominator for these are actually derived from whether they are reactants or products, and you could also now look at what's the loss relatively speaking. 1 mole of hydrogen is lost with half a mole of oxygen that is lost to produce 1 mole of water. So that's what we write. So if you now consider a general reaction like an algebraic form that we have considered before, except we now write nu I single prime script mi gives sigma I equals 1 n nu I double prime script mi. So previously we had a ni single prime and an ni double prime. We have switched to nu I. Suddenly we became Greek. Yeah, there is a reason for this. We will now get into the difference between what's called as a order of the reaction and molecularity of the reaction. So if you're now thinking something like half, it refers to something like number of moles, but if you're looking at a reaction that's happening at the molecular level, you can't have like half a molecule react with another molecule. Okay, when you're looking at molecules and atoms colliding with each other, right? So half a molecule cannot react as if it's half-hearted or something like that, right? So a molecule reacts, molecule reacts. So we will try to make the distinction over there, but as far as what we are doing now, since we have a half here, you could stick to our notion of number of moles for the coefficients here, okay, which could be now taken care of by a nu I single prime and a nu I double prime as before, which was done by ni single prime and ni double prime. And if you want to now write a set of equations like this is actually a set of equations. This is actually a set of 3 equations for 3 reactants, three species there. So similarly, you could for n species, you could now write n equations, right? And the way we would do is, since we have actually accounted for all the n species on either side with a nu I single prime and a nu I double prime, and we know that if something is a reactant, the nu I single prime is non-zero and the nu I double prime is 0, and if something is a product, its nu I single prime is 0 and nu I double prime is non-zero. So taking that into account, you simply have to take its double prime minus its single prime to get you the right sign as well. You can get a negative sign if this is 0 and that is non-zero, okay, and you get a positive sign if this is non-zero and this is 0. It doesn't have to be exactly zeros as well. You could have like excess reactant that goes to the product side, which will be of a lesser value in terms of stoichiometric coefficient than on the right hand side. Then you get a positive value, so negative value here as well. Okay, so all that stuff will be taken care of by this notation. And then what do you do with all these things that are equal to each other? Okay, so we now say all these things that are equal to each other could finally be equal to a elemental change in a quantity called psi. Yeah, so we now say this is equal to d psi, where psi refers to psi refers to degree of advancement of the reaction, right. So it tells you how much of the reaction has proceeded depending upon how much elemental change in the number of moles has been effected for each of the species. Okay, so now you divide the above equation by volume. That means you now look at whatever is happening per unit volume V, right. So N over V is equal to C, which is the molar concentration, therefore dN over V is equal to dC, and look at the time rate of change, right. That is to say dN over dt per unit volume is essentially dC over dt, right. Now this is very significant here. Ultimately what we are looking at is the rate of change, the time rate of change of concentration of a species, of any species, okay. So of course when you are now saying N, it means the total number of moles, but you could, if you put a subscript I, that refers to the number of moles of species I, yeah. So you could do the same thing for any of those. Therefore we can now do this for all of these. That means you divide the entire set of equations by volume and then take the time rate of change in each case, then you now get dC1 over dt divided by nu1 double prime minus nu1 single prime equals dC2 over dt divided by nu2 double prime minus nu2 single prime, etc. For the general case of the ith species, dCi over dt divided by nu I double prime minus nu I single prime up to dCn over dt divided by nu n double prime minus nu I single prime, nu n single prime. So what happens finally, right? So you now have a d psi over dt divided by volume, right? So you now have okay. So this is what we would like to call as omega, which stands for the reaction rate, right. In that sense, the reaction rate is a term that is common to a reaction, alright. It's you now you are given a reaction, that means it will have a reaction rate, okay. What is it the rate of? Well, what are we trying to measure out of this? Actually it is something that is common to all the species. Strictly speaking, what we should be asking or be interested in is what is the rate of production or depletion of a particular species, okay. That is given by dC1 by dt, dC2 by dt, etc. And therefore dC1 by dt will be nu1 double prime minus nu1 single prime times omega, and so on for each of those species, right. So that's exactly, so you have like a common quantity reaction rate from which you will now get the rate of production or depletion of the individual species. That's how we try to go about doing this. So what does this really mean? It's essentially a volumetric time rate of change of the degree of advancement of the reaction. So that the reaction rate essentially means a the rate of change of the degree of advancement of the reaction per unit volume. So keep in mind there are two things about a reaction rate. This is very important for you to think about all the time. Whenever you are bringing in reactions into picture, the reaction rate is going to come into picture, and correspondingly the rate of production or depletion of individual species. It's always per unit time per unit volume. Okay, it's volumetric rate. Volumetric means per unit volume, rate means per unit time. Okay, so these two things are always there, and typically in SI units, if you're interested in putting this in things like mass balance and so on, we are always looking at measuring this in terms of kilograms per second per meter cubed, right. That's what we are looking at, we are beginning to look at. At the moment, of course, we are now having a omega here, which is essentially looking at the change in the number of moles per unit time. So there's moles per unit time per unit volume. It's not yet kilograms, right. So that means we have to now throw in a molecular weight. So you can't do that for a common reaction rate, the reaction rate that's common to all the reactions. You could do so for the individual species, because individual species will have individual molecular weights. So you can throw in molecular weights for individual species to convert the rate of change of number of moles of those species to the rate of change of mass of those species, right. That's what we will do ultimately, but I'm just trying to tell you what's all coming ahead, and what are the important things that we have to keep thinking about. So if you now keep that along with that line, so in general we can say dci over dt, if this is actually omega I, this is the rate of production or depletion, in fact we should say net rate of production and depletion of species I, right, species I, net rate of production of, I will explain why we are saying net in a few minutes. Essentially what you are thinking is not just one reaction here, we will now try to have a sequence of reactions in which a species could be produced in one reaction and could be consumed in another reaction. Okay, so there is like a net rate of production and depletion. So that's what the word net would mean, and we will see this a little bit more explicitly. But essentially what we are now saying is, therefore omega I is nu I single prime double prime minus nu I single prime times omega. Okay, so where are we? We are supposed to, in this framework we should now be able to write out the law of mass action. So the law of mass action, the law of mass action states that, right, I'm not going to write long sentences like you go through in high school, that's the difference now. States simply that omega equal to k pi I equals 1 to n ci to the nu I single prime. This is what you have actually learnt in high school. Okay, now it's all put in algebraic form. So this simply means that so long as you use a nu I single prime as the exponent over there to ci, what it simply means is the rate of reaction, the common quantity for all the species that are participating in a reaction, yeah, is equal to a what's called as a rate constant or a specific rate constant. Okay, it's not a constant, we will now expand on that a little bit more time, but it's like a proportionality constant. So effectively we are saying the rate of reaction is proportional to the concentrations of the reactants raised to their stoichiometric coefficients, right. So when you say reactants, that means we are looking at nu I single prime. Keep in mind you are taking like a product of all the species, So if some of the species are actually products, the nu I single primes for them will be 0, therefore they don't really contribute. You now have Ci to the nu I single prime for them to be equal to 1, and therefore you don't have to worry about it. Yeah, so it's pretty general expression there. And the next thing that I would like to point out is K here, K is equal to A e to the minus E over RUT. Sometimes there is a subscript A to E here, so to indicate its activation energy, but it's essentially activation energy there. So e to the exponential to the negative E over RUT. RU stands for universal gas constant. Right, in the Arrhenius, so this is what is called as the Arrhenius law. The Arrhenius law essentially gives you the temperature dependence of the rate constant, or rate constant is also called specific reaction rate. Okay, it is essentially the reaction rate for unity concentrations of the reactants. So that's why it's called specific reaction rate, but it's also called the rate constant, but it's not really a constant, it depends on the temperature. And the Arrhenius law essentially gives you the temperature dependence. You could also write this if you want to now include many times K equals B T power m e to the minus E over RUT is also used. That means there is a polynomial dependence of the rate constant on temperature, that's T to the m, and there is a exponential dependence on temperature. Okay, so the exponential dependence obviously is a lot stronger dependence when compared to the polynomial dependence. So sometimes you could tend to ignore it and say let's not worry about the polynomial dependence, let's simply say take it as A to the minus E over RT, right, and there you are taking in only the exponential dependence. The exponential dependence is the biggest problem with combustion. So what we are actually now going through is in some sense like is one of the biggest stumbling blocks in solving combustion problems. Okay. The exponential dependence is a highly nonlinear dependence. Okay. So essentially this is what, and depending upon the value of E, and typically when the value of E is larger and larger, the nonlinearity, the nonlinear dependence of K or the reaction rate in general on temperature becomes more and more nonlinear. Okay, so it becomes very sensitive to temperature. That means it doesn't change over a fairly wide range of temperatures, but you now cross a certain threshold temperature, it just goes boom. And what that means is we should now be able to capture this variation within that very small change in temperature, because this suddenly changed. Until then you don't have any reactions happen, significantly speaking, right, and all of a sudden you have all the reactions happening. Okay, so there are very quick changes that keep happening in space or in time, depending upon whether you're looking at unsteady problems or both. Okay, so you typically also have a very spatial resolution issue because of these things, and this poses a what's called mathematically what's called a stiff situation. So because when you're now looking at convection in a flow and then you have a flame, and then suddenly when you go to the flame you're now having a sudden increase in temperature, right, and so long we have not been having such a high variation in temperature. So you're okay with resolving the temperature over larger distances, and then suddenly over here where the flame is you now have to resolve very close, and now begin to keep track of these fast changes in temperature. if you were to do the same thing over there, it's sort of like there is hardly much change, so you're wasting your time doing that. Okay, so like for example, if you do computational methods, you would want to take like a very coarse grid, relatively speaking, over there, but when you get to the flame you want to now suddenly have a very fine grid, but you're supposed to find out where the flame is, and therefore you should adapt your grid and stuff, so it's difficult, right. So typically you now have a much different length scale for combustion than for reactions. So if in the same equation, as we will see, both the reactions and the convective processes occur and they are happening at two different length scales, it's very difficult to resolve both of them with the same scale, right, and that's typically what's called as a mathematically stiff problem, and you'll get into these stiff problems primarily coming out of this here, right. So we are just beginning to get into the gory details of combustion, if you will, yeah, there. Okay, so let me just box this for you to make it look good. One of the things that I would like to say is, whenever you are dealing with the Arrhenius law, you are always using the universal gas constant. Never make a mistake, never have any confusion about this. Okay, so typically when you're busy writing an exam, you're like, do I use the specific gas constant or the universal gas constant? Well, what do you do now? No, Arrhenius always uses the universal gas constant. Okay, so this is something that you always keep in your mind when you're doing like back of the envelope calculations, exam problems, and so on. Okay, second point, in this course we are now going to take these as laws. That means we are not going to ask how we got these. Okay, how did you get these? Did experiments? Hey, I guess, yeah. So somebody actually took beakers, poured things, stirred up, and started measuring things. Is that how they figured? Yes, that's true. They did that. Okay. Plus, you could also have a quantum mechanical basis for this. For example, this is what's called the A or B. Okay, so now you can call this exponential factor, pre-exponential factor, right. So from quantum mechanics we will be able to find out that this actually depends on probability of what's called as effective collisions. Okay, so what is meant by effective collisions? What it really means is you need to have molecules that collide actually come in at a particular orientation with respect to each other. So it's like you have a molecule, that means it has a bunch of atoms in a particular arrangement. You have another molecule of atoms, its atoms in a particular arrangement. When you now have a reaction that's going on, it's one atom of this molecule and another atom of the other molecule that are the ones that are actually exchanging electrons and creating bonds there and then disrupting other bonds there, right. That means when they collide, you need to have this particular atom of this molecule collide with that particular atom of that molecule. That means they should be oriented in particular ways, right, and the probability with which they would orient in those particular ways is less when compared to if you didn't have to worry about the orientation, right. So all that stuff is buried in the pre-exponential factor. Okay, so you can derive these things from quantum mechanical basis, and a good graduate course would do this, right, or we would have a we have another course like physical gas dynamics where you can actually go through all these things, yeah. So that's typically taught in the odd semester, that's like the ongoing semester now, so you can sit in a course there where you can learn all these things. But in this course we are now going to keep on adopting the continuum approach. That means at a particular point you have a temperature that is defined, you have a concentration that is defined, and based on the concentrations the reaction rates are going to be determined, and based on the temperature there the reaction rate constant is going to be determined by given by these laws. In reality, at every point in space where you have reactions happening, you have like millions of molecules that are bombarding each other and going through reactions. We are not resolving that level of detail. Yes. We don't want to define that in this course. Right? So one of the things that we go through in chemistry is something like a hill that you have to cross, and then there is like a height of the hill, that is activation energy. We don't want to worry about all that stuff. Okay? So because of this, mathematically speaking, you will also face a problem in thinking about ignition, because if this is your, think about this, if this is your K, you now plug this in K, and then you now get your omega, right, and plug the omega in here, you get an omega I, which is the rate of production of a particular species, right. Now let us suppose that we have a methane oxidation reaction that you are thinking about, and let us do something very sinister, right. This is something that I always do. Fill up this room with methane, yeah, and of course we have some oxygen, otherwise we won't be breathing here, right. What's going to happen? Are there reactions going on or not? I just filled up this room with a decent amount of methane. Are there reactions going on? Oxygen is there, right? According to this, yes, right. So of course we have air conditioning and all those things, so the temperature here may be like about what, 20 degrees C, right. So you are looking at like, you plug in 293 K over there, right. You will now get some value for different values of A, E and so on, and you plug it in there. I will tell you what the concentration of the methane is, what the concentration of oxygen is, plug it in there, and then you know the reactions, the nu I double prime and nu I single prime. Then you can find out the rate of production of carbon dioxide, or rate of production of water, or rate of depletion of methane, all these things, right. You will find some values which are non-zero. What do? That means you just fill in some methane in here, reactions are going to go on. Hey, that's dangerous, huh? What's happening? I haven't yet ignited. That means we don't have a flame that is propagating. We aren't burning yet, right? And we are still at 293 Kelvin, 20 degrees C. So, but there are reactions going on. Any idea of this number? Like what would be your omega? That would be extremely low, 10 to the minus 14, minus 15, that kind of thing for room temperatures. Okay, so from a mathematical point of view, what this actually means, and we will relate this to what's called the cold boundary difficulty. Okay, that means we really strictly speaking cannot identify reactants as completely reactants. Okay, because even as they are just being reactants, they strictly speaking in principle should be reacting and producing products at a very minuscule rate according to this, right. It becomes numerically significant when the temperature rises past a value that is like related to E over R or U. Okay, that is what this means. Then you begin to have values that are significant, the heat release that is significant. It begins to hurt us, okay, and then we get burnt. Okay, so keep this in mind. We are not going to worry about what E means to us, except to point out that the value of it is going to dictate the non-linearity of the reaction rates dependence on temperature. Okay, that is what we want to worry about as far as we are concerned. Okay. Typically when you have a full-fledged reaction that is going on and you think that you have a flame there, the reaction rates are very high, of the order of it could be even 10 to the 10, right. So we are now going from one end to like 10 to the minus 10 to 10 to the 10. So that's another thing. So as I told you, we are not only having like a very narrow region over the steep rise happens, but the steep rise happens over a huge range. So you have to capture this numerically, the values. That's very difficult. So that's the biggest problem as far as combustion is concerned. The chemistry that is thrown in there, the exponential dependence of the reaction rate on temperature is the biggest villain in chemistry. Okay, that makes the whole problem highly nonlinear and very stiff. So I guess I can't emphasize enough about this, but we'll just move on, and then we now say for a system of reactions, so how do you write a system of reactions? You now say sigma I equals 1 to n nu I k single prime mi gives sigma I equals 1 to n nu I k double prime mi k equal to 1 to m. So capital M indicates the number of reactions that you are going to have, right, in a scheme of reactions, and each of those reactions then, the kth reaction, will be identical to any of the single reactions that we have seen before, okay, except we now want to identify the stoichiometric coefficients with the kth reaction as well as the ith species. So we now say it has two subscripts, nu ik single prime and nu ik double prime. These now become like matrices. Okay, so this then means that you are looking at a multi-step reaction sequence. Why would you worry about a system of reactions or a multi-step chemistry? The reason is, as I told you some time back, a species that is produced in one reaction could be consumed in another reaction. So the net production, the net rate of production of or depletion of a species will now be dependent on how much is produced in each of the chemical reactions, right. So that's what we are going to keep track of. So we have for a system of reactions notated by this, we have omega k. We now have the common quantity reaction rate now specific for the kth reaction. Okay, so the kth reaction, the reaction rate for the kth reaction is equal to kk pi I equals 1 to n ci nu omega ik single prime, okay, and that's equal to ak e to the minus ek over RUT pi I equals 1 to n ci nu ik single prime, right. Well, if you want to do one more, bk t to the mk e to the minus ek over RUT pi I equals 1 to n ci to the nu ik single prime. So look at what's going on. We are now having a sudden explosion of the number of parameters that we have to consider. Okay, so previously I said these are going to be given to us. Okay, so when you now have a reaction, you know what the nu I single prime and nu I double primes are. So that was given to you. So we are looking at what this was, and that's given by this reaction. That means we need to be supplied with these two values, A and E. Okay, if you now want to further take the polynomial dependence on temperature, then you need to have B, M and E. Okay, so for a given reaction you need to be given B, M and E these are what's called the kinetic parameters, okay, and the information on nu I single prime and nu I double prime is essentially giving you what the reaction is, okay. It's a capital N, and what the script MI's are, the nu I and nu I single prime and nu I double prime is what's going to give you what the reaction is. In the system of reactions, your capital N, capital M, the script MI's and the nu I single primes, nu I k single primes and nu I k double primes, all this information gives you what's called as a reaction scheme. The reaction scheme is nothing but a list of reactions, okay. So when you see the list of reactions, you should be able to find out what is the capital N, what's the total number of species, okay, and I going from 1 to n, what are the species, script Mi, and how many reactions are there, capital M, okay. K going from 1 to m, what are the reactions, that's given by that will be identified by nu I k single prime and nu I k double prime, or we should be able to deduce all those things given a scheme of reactions. But that's only one part of the story. That's only telling you what is the chemistry, right. This species reacted with this species to produce that species and that else, and then some of those species reacted with this, blah blah blah, and then so you have a scheme. Then there is another part of the story. So one thing is to actually figure out the chemistry, the other thing is to actually figure out BK, MK and EK for each of those kth reactions. These are the chemical kinetic parameters, okay. So chemical kinetic parameters many times are quite difficult to measure and obtain, even if you were to figure out the reaction scheme, you see. So what we, and then most of the time the combustion expert or the combustion scientist tries to bank on a chemist to give this information. So you have to actually get this information from a chemistry person. First of all, find out what the chemistry is, that means what is the reaction scheme, that will give you the nu I single k, nu I k single prime, nu I k double prime, script MI's for I going from 1 to capital N, what is capital N and what is capital M, all these things. That's only the scheme. In addition to this, we have to get BK, MK and EK, these three parameters for each of the reactions. That's a killer. Many times you get into a problem there. So here, just to record whatever I'm saying, this is the specific reaction rate of kth reaction, and right now omega I remains the same as what we had before, right. Omega I is the net rate of production or depletion of species I, net rate of production or depletion of species I. This will be equal to sigma k equals 1 to capital M omega ik. So where omega ik is rate of production or depletion of the ith species in the kth reaction. That means in every reaction you have some rate of production or depletion of each species, right. That's omega ik. You sum over all the reactions to find out. So in one reaction omega ik could be positive, another reaction omega I could be negative. If it is negative, that means it's depleting there. If it's positive, it's being produced there. You know, add up all that stuff algebraically, right. You should now get the net rate of production of that particular species, and that's what we will care about. The reason we will care about that is because just like how we normally do a mass conservation, okay, in your fluid mechanics, in addition to doing mass conservation for the mixture of species, we will also now do a mass conservation for every species. Now obviously each of the species mass doesn't remain constant, so to conserve doesn't mean it's going to be a constant, okay. What it means is whatever is the rate of change of mass will be equal to the net rate of production or depletion. That's what we will do as we go along. So we will factor this into the mass conservation equation of individual species as a next step. So this is going to be very, very important to us, yeah. So omega ik then is equal to nu ik double prime minus nu ik single prime omega k. That's like the multi-step version of this over here, right. We did this only for one reaction, we now do this for the kth reaction in a multi-reaction step. Now you have to plug this back in here, add over all the reactions to get the net rate of production of a particular species, right. So therefore omega I equal to, this is nothing but dCi over dt, that remains the same there, you see omega I is dCi over dt, right. So dCi over dt, that's equal to sigma k equals 1 to m nu ik double prime minus nu ik single prime omega k, and omega k is bk t to the mk e exponential minus ek over ru t pi j equals 1 to n. I am just using a different running variable just to avoid confusion, cj to the nu j k single prime, right. What do we have here? What do we have here? You now say dCi over dt is equal to a lot of things all now put together. So we just started learning something, and then pretty soon we now have all of them collapsed together, right, in one line, and finally we now have a dCi over dt going all the way. You have a pi j equals 1 to n cj to the nu j k single prime, okay, which means this contains a product of all the species which are reactants, right, in the kth reaction, and you now sum over all the k reactions. So pretty much all species concentrations are now going to figure in here, right, as product in one term, and then you are going to have many of those terms added up for each of the reactions, right. So you will now have dCi over dt for the ith species equal to one term plus another term plus another term and so on. Each of those terms is for each reaction, and each term contains products of species concentrations, possibly of the same species for which we wrote the dCi by dt. So two things are emerging here. One, the rate of change of concentration of species I depends on the concentrations of all species practically or in general. That means you can't evaluate the rate of change of concentration of species I independent of all other species. You have to know the concentrations of all species to be able to find out what's the rate of change of this, right. This means you now have for this box we should be able to write I equals 1 to n. That means this is actually n reactions for each species, So n equations for each species, right, and all these equations are simultaneous set of equations, they are all coupled to each other, because the rate of change of this is going to depend on all other concentrations. To find out the rate of change of, so if you want to find out Ci, you now do a time integration of this, right. So if I were to give the concentrations that are initially present for a set of reactions, right, from there I should now be able to do a time integration. So I now integrate this in time to go to the next step, next time, okay. During this time a lot of species would have got consumed, a lot of species would have got produced, all those things are actually present over here. That means I have to solve the next dc by dt for the next species and so on. So all of them should be solved simultaneously. So it is a simultaneous set of first order ordinary differential equations which we have to integrate in time simultaneously for all of them, right. This is only the starting, we are only scratching the surface here. Now look at the nature of these equations. The nature of the equations is, first of all, these are highly nonlinear, not because of the hue and cry that I made about the temperature dependence, that is the nonlinearity in the temperature dependence, that's showing up here, okay, in each of these terms. That's bad enough, that's something that I will come to next, okay. The nonlinearity is because you now have each of these Ci's as an unknown you have to solve for simultaneously, and these unknowns are actually showing up as products, right. So anytime you have products of unknowns you have nonlinear equations, right, and not only that, even if they didn't show up as products they are raised to possibly a non-unity exponent, right. So anytime you have like a square or cube or minus 0.1, anything other than 1 is nonlinear. Okay, so linear is only one thing which is like 1, okay, nonlinear means anything else, right, that's going to screw up your day and make it nonlinear, right. So you already have a nonlinear set of first order ODEs here, and then on top of this we will have to find out, in reality, in real combustion applications we won't know what the temperature is, okay, and the temperature keeps changing from place to place or time to time or both place and time. That means we have to now have another equation that governs temperature, and that equation also will be coupled with this equation, because in order to solve that equation you needed to know what was the heat that was produced by these reactions to change the temperature, and we will see that as we go along. And in order for you to solve this, solve this equation, you need to know the temperature. So in addition to this n equations that are getting coupled, you will also have an energy equation that gets coupled with this, okay, because the temperature is coupled to the species and the species are coupled to the temperature, okay. But if you are given temperature, it's possible for you to, so let us say you are now taking like a bath that is now maintained at a particular temperature, and you wanted to know what should be the concentration of species that are produced given an initial set of species. This is an initial value problem because it's a ODE in time, right. That means you can integrate in time given initial conditions for the concentrations of the species, you should now be able to advance in time. So if given temperature, the energy equation gets decoupled from this set of equations, but in a real practical problem you will have both of them coupled, and this becomes a nasty set of equations as it is, without even worrying about convection and diffusion of species yet. So we are now beginning to look at combustion, like, right, it just becomes gory and gory by the minute from here on. See you tomorrow.